Hi, year 13. So, retrieval roulette, get your book out and get these answered for me, please. Okay, hopefully you have that done by now. Okay, so here's your answers. The superconductor curve is here. Just make sure that you are marking on the critical temperature. I've drawn this here a bit shallow actually, so this can be drawn really steep or even vertical. And then just make sure that this bit here is just increasing with temperature. Okay, so pause, get the rest of those marked for me please, and thank you. Okay, now turn to page 138 in your notes for me please. We're going to start looking at the equations of motion today, so that's good. Now, just like speed equals distance over time can only be used if something's travelling at a constant speed, or to calculate the average speed, like the equivalent constant speed that something would be travelling at. The equations of motion really are called the equations of uniformly accelerated motion. So they only can be used if something's accelerating at a uniform rate. So if you have, oh hold on, this is distracting me, I'll get rid of this. So if you have like your velocity time graph and it's a curve, which remember means the rate of acceleration is changing, then you cannot use the equations of motion. They only apply whenever the acceleration is constant, either a constant acceleration or a constant deceleration. We never do non-constant, I can't think of the proper word for that, acceleration in physics. You do that in maths at some stage, but we don't do it in physics, okay? So these equations of motion are just equations which always work if something's travelling at a constant acceleration. Now, I'm not going to read through all these notes here, but I do want you to read through them. It's just showing how the equations of motion can be derived from a velocity time graph for a particular journey. Now, these are derived slightly differently for you in maths, I know that, but I think this shows nice and clearly where the equations come from. Okay, so I do want you to have a read. So the equations, V equals U plus AT, most commonly used one, S equals UT plus a half AT squared, and S equals V plus U over 2 multiplied by T, and then V squared equals U squared plus 2AS. Now, two of these are equations that you learn in year 11, okay? So V equals U plus AT is really just the acceleration equation, A equals V minus U over T, right? This one is really just distance equals average speed times time, or displacement equals average velocity multiplied by time, because if I look at just this little section over here, we're adding two values together and we're dividing by 2. So we're finding the average of these two values. And they are both velocities. So if we add them together and divide by 2, we're going to calculate the average of them. So S displacement equals average velocity multiplied by time. So that's one that you technically already know is already. So these other two, you're just going to have to learn if you don't know them yet. Okay, so I've just realised I haven't even told you what the letters stand for. So if something is changing velocity, we use the letter U to represent its initial velocity, so the velocity at the start of the particular situation that we're looking at. V is the final velocity for that particular situation. A, acceleration, S, displacement, and T, time. So these set of values can be used for a whole journey or for just one wee section of a journey, and you're more likely to use the sections of a journey if it's like something that's thrown up and then cut down again. You can split that into two, and then it gives you a wee bit more information about it. Okay, anyway, back up to the top of page 140 for me please. There's a couple of wee things I want you to change. Don't like the way I've got this written, sorry. So vertical motion under gravity. So an object dropped will accelerate due to the pull of gravity. I just want you to change that, right? Fussy about it. Even though, yeah, anyway. However, weight is not the only force acting on a falling object. Air resistance is going to act upwards, opposing the motion. So that's just if something's going down the way, air resistance is going to be acting against the motion. So we describe an object as in free fall if the only force acting on it is due to gravity. So if the only force acting on it is weight, and a lot of the questions that we will deal with will be assuming free fall. So like we kind of act like air resistance doesn't exist a lot of the time. All objects in free fall accelerate downwards at the same rate. Now be careful, in physics we use 9.81 meters per second squared for gravity. I know in maths we use 9.8, sorry. The acceleration does not depend on the mass of the object. Okay, things you need to remember then. So what all the letters stand for. You'll hear me referring to these a lot as you've asked questions, and it's just because of this. I think that's probably a bad habit that I refer to them as that, but there you are. So if you're starting off a question, always make this little list of information, and quite often just you'll need to make a note of what way you're taking as being positive. Anyway, I'll just work my way through the list instead of going off the top of my head. So if an object is starting from rest, can you add in this for me please? So sometimes it's not 100% obvious that it's starting from rest, so if something's being dropped, then it is starting from rest. However, there's a question that's coming up that catches people out all the time. So say it is, I think it's like a hot air balloon or something. So say this is the hot air balloon and this pen is going to get dropped from it. Okay. If the hot air balloon is going up and then someone drops the pen, I did a terrible demonstration of that. Let me try it again. So if it's going up and then someone drops the pen, the instant that the pen is dropped, it has an upwards velocity of whatever the hot air balloon was going up with. Okay, so say this was going up at 5 meters per second, right? As soon as this gets dropped, it was going up at 5 meters per second, so it's going to be decelerating from that like decelerating and then accelerating rather than starting from zero. So just look out for little things like that. Okay. Oh, I didn't even finish this. So if an object is finishing at rest, then V is going to be 0. We sneaky one for that is if it's something that is thrown up in the air at the very, very top of its flight, its velocity is 0. It stops for a very brief second. So that's what I was meaning whenever I was saying you can split journeys up into sections, because it gives you a little bit of extra information. Like, say I throw this pen up and then catch it again. If I only look at the first half of that journey up until the top, then that gives me an extra piece of information because I know that final velocity up there is 0. Okay. Just be careful whenever you're reading information from questions. Now, if you are doing maths this year, then you will be able to rhyme these equations off the top of your head already. If not, then at the very start, until you get to know them off by heart, write them all out at the start of a question, or even write them all on a post-it and have that beside you, because that will make the picking what equation to use process an awful lot easier. Okay, so it may help to write out all 4 questions when beginning a question. This will make it easier to choose which one to use. Unless told otherwise, take acceleration due to gravity to be 9.81 meters per second squared. The textbook that we use quite often tells you to use 10, which does my head in, but there you go. In exams, unless they tell you otherwise, it'll be 9.81. So as always, be careful with your units, keep them consistent. SI units, quite often there's a value that needs to be converted. Drawing a wee quick sketch to help visualise the situation is invaluable. And I don't mean anything fancy, it can be a couple of lines on a page, but if it helps you like visualise what's going on, it's priceless. Is that the right word? No. Pick one direction to be positive and then stick to that throughout the whole question. And then check your answer's sensible. So if you end up with a man running at 5,796 meters per second, something's gone wrong. Okay, over on to 141, and we'll start to work through these examples here. Okay, so a tap drips into a sink which is 40 centimeters below the end of the tap. How long does it take each drop to fall? So before I start, I'm making my UVAS list. So tap dripping, that's like being dropped, so the initial velocity is 0. We do not know the final velocity. Acceleration is going to be due to gravity, so it's 9.81 meters per second squared. As I'm writing that in, I'm taking it's making me realise sort of that I'm taking down the way it's being positive, which I think is obvious enough for a question like this because nothing's changing direction. Now, the sink is 40 centimetres below the end of the tap, so the displacement that we're talking about here is 0.4 metres. And the question's asking us for how long does it take, it's asking us for the time. Now, this may seem silly, but I only put a wee question mark at the thing that the question's asking me for. It hasn't mentioned this final velocity, I don't need to figure it out. If I put a question mark in there, then it's almost like information overload, and it makes it harder to figure out what equation to use. Because I literally have nothing there, no value, no question mark, it means I can ignore V. So my thought process for picking what equation to use is, right, I need something that links U, A, S and T. That's S equals UT plus a half AT squared. Okay. Hopefully you see what I mean by that, and I know it may seem trivial, but honestly, I promise it helps, or I think it does anyway. Next, fill in my values. So S is 0.4. U is 0, so anything multiplied by 0 is going to give me 0, so I'm just going to put in 0 there. Plus half multiplied by A, which is 9.81, and then multiplied by T squared. So 0.4 is 4.905 T squared. Divide both sides by 4.905, gets 0.0815. And then square root both sides, and I'm going to swap the sides as well. Gets me 0.29 seconds. Okay, hopefully that one was okay. Okay, example 2 over the page then. So a stone falls vertically for 2 seconds and embeds itself 2 centimetres in soft mud. What is its average deceleration in the mud? So this is one that has to be split into 2 parts. Okay, so a wee sketch is going to help me out here. So that line here is the start of the mud. So here's my stone, and it's being dropped, and it's going to fall down here. So its starting velocity here is 0 because it's being dropped. I'm going to call this section 1, like in the air, and then section 2 is in the mud. So we're going to be able to use this information to figure out the speed that it hits the mud at, because that's going to be like the connecting factor, because the final velocity for section 1 is going to be the starting velocity for section 2, whatever speed it hits the mud at. That's going to be the starting velocity for the wee mud scenario. So in here, then it's going to come to a stop, which means its final velocity in this little section is 0, and that was 2 centimetres. What did we know? We knew the time for the air, didn't we? Yeah, so it took 2 seconds to do that. I don't really know how to mark that on my diagram very well. So, can you make a wee note here that V for section 1 is U for section 2? Okay, do that. So if we were to sort of spoilered it for you, sorry, by telling you that this is like what we're going to have to do, but if we were to look just at the mud, we have S, we have V, we're being asked for A, really. I know it's a deceleration, but we're being asked for A. We don't have enough information, so we need to be able to use this first section to get another bit of information, right? And that's as always, it's the thought process about where to start with these that can sometimes make them tricky. So if we look at section 1, right, in the air, I'm going to take down as being positive, and I'm going to make my UVAS list. So for section 1, the wee bit in the air, U is 0. I'm going to use it to find V, so I'm going to put my question mark there. A, 9.81, because it's due to gravity. We don't know how far it fell, but we do know it was falling for 2 seconds. So we're looking for what links U, V, A and T. V equals U plus AT. So all I'm doing here is substituting in my values. So I get 19.62 meters per second. So now I know about section 2. So I'm still going to be taking downwards as being positive, okay? If I make my UVAS list, now I know that my starting velocity in the mud here is 19.62. So this wee stone decelerates from 19.62 to 0, and it does that in 2 centimeters. So S is 2 centimeters, and this question has asked us for the deceleration, so we have to find A. So I know I can ignore T, so I'm thinking, right, what links U, V, A and S? V squared equals U squared plus 2AS. Now, these questions are so much easier whenever you can, or whenever you know the equations of motion off by heart, right? So if you're not at that stage yet, work to be at that stage, because it makes it 10 times easier. So V is 0, so 0 squared is 0, equals 19.62 squared plus 2 multiplied by A multiplied by 2. So let me just tidy up here. If I bring this over here, minus 4A equals 19.62 squared, then divide this by minus 4. Oh, have you noticed what I've done wrong? I hope you have. I haven't changed this to meters, hold on. Okay, what an idiot, sorry. You can just watch me change it. So 0.02 meters. These should both be 0.02. Oh jeepers, okay. Okay, so 0.02, 0.02, 0.04 minus 0.04, sorry. Anyway, 19.60 squared divided by minus 0.04 gets minus 9623.6 meters per second squared, which seems crazy high, but like this thing's going at 19, so 20, basically 20 meters per second, and stops in 2 centimeters. So it is going to be a really high deceleration. So our deceleration is going to be just positive that. Okay. Terribly sorry about my silly mistake. That's one of the things on my list too. What an idiot. Right, example 3 we're not doing. We're going to change it for a better one. I'll write it in now. Okay, pause, write that question in, and then we'll work through it. Now, I think this was one I just made up on a whim last year in class, and then it ended up being way more awkward than I was expecting, which is good. Okay, so a ball is thrown upwards with a velocity of 5 meters per second from a height of 25 meters above the ground. Calculate the time taken for the ball to hit the ground. So, well, it's not actually that awkward. I think it's just if you try and solve it one way, there's like a real sneaky wee thing you have to be careful of. So this is like the platform I've just drawn that the ball's getting thrown from. So this is 25 meters tall, and this ball gets thrown up, and then it's going to end up coming right the way down to the ground. So I'm going to split this into 2 sections, right? Up to the top from here is going to be section 1, and from the top to the bottom is going to be section 2. Okay, and it's thrown up with a velocity of 5 meters per second. I've drawn that too small to mark it on. Mark it on yours if you want. Okay. Right, so what's this asking us for? The time taken for the ball to hit the ground. So that's going to be the time to get from here to here and the time to get from here to here added together. So let's just start off by looking at section 1. In section 1, I'm going to take upwards as being positive just because it's going upwards. Hope you don't regret it. So you've asked, it is thrown upwards with a velocity of 5 meters per second. So because I've taken up as being positive, I put this in as positive 5. For section 1, it's up until the top of the flight, so V is 0. A is going to be decelerating due to gravity, so it's minus 9.81. S, I don't know, time is what I'm trying to figure out. So U, V, A and T, V equals U plus AT. V is 0, U is 5, minus 9.81 T. So bring this over that side, 9.81 T is 5, that gets 0.51 seconds. Okay. This we're going to end up using, so I'll draw a wee box around it. Now, I know I'm going to end up needing to get a wee bit more information for this, but I'm going to act as if I don't know that yet, okay? So if we look at section 2, this time I'm going to take downwards as being positive, and it is okay to switch like that in a question. You just need to be super careful that for everything that you do with this, you're consistent. For everything that you do with this, you're consistent. So be careful, okay? So UVAST, U for this wee section 2 is 0. It starts from 0 at the top. We don't know what speed it hits the ground at. We do know it's accelerating downwards, and I'm taking downwards as being positive, so that's 9.81. We don't know how far it's falling, and we're being asked for the time. So we don't have enough information here to figure this out. We're going to need an extra bit of information, and the information that we can get is S, because we know from here to here is 25. So we can use this first section to figure out this displacement here, and then add that on to the 25 to get this one. So back up to section 1, let's figure out S. V squared equals U squared plus 2AS. Yeah. So V is 0, U is 5, 2 times minus 9.81 times S. I don't actually have this done because I did it a different way last year. So 0 equals 25 minus, what's that, 19.62? Yeah. So 19.62S is 25, 1.27, yeah. Okay, so that means that S for this wee section 2 is 1.27, which is from here to here, plus that 25. So this S is going to be 26.27. Okay, so now we've got enough information. We've got UAS and we're looking for T. So S equals UT plus a half AT squared. So fill in the values, 26.27 for S, U is 0, so that's all going to disappear, plus half times 9.81 times T squared. Divide both sides by 4.905. What's that get? 5.36. Square root both sides, 2.31. So add them both together and then we've got our total time. So 0.51 plus 2.31, what's that get me? 2.82. And that is our final answer. So I quite like that wee one because it emphasises a few points, like splitting into sections is good, being super careful with direction is good, and all of that. Okay. What I would like you to do now is page 144, questions 1 to 4. You can leave out 5, okay? So just questions 1 to 4. And that's us. I'll see you next day.